Ever stand on the beach and feel like the ocean's putting on this show just for you? We're diving into the wild world of waves today, and trust me, it's way more than just water moving up and down.
That's right. We're gonna uncover some seriously mind-bending physics, all thanks to the legendary Richard Feynman and his knack for explaining like the complex in a way that makes you feel like a kid again.
We're working with excerpts from his Feynman lectures on physics, and let me tell you, the man, he had a way with words. Get ready to see waves breaking all the rules you thought you knew, starting with a sonic boom.
Now there's a sound you don't forget.
Exactly. But have you ever actually stopped to think about what's actually happening when a jet like breaks the sound barrier?
It's not just about the noise itself. Imagine this: the jet is moving so fast
Yeah.
that it's actually outrunning the sound waves. It's creating.
Right, hold up. How can something outpace its own sound?
Think of it like this: every instant, the jet it emits sound waves, but because it's traveling faster than those waves can, propagate, they get compressed. They bunch up, forming a cone. With the jet at the tip, that cone is the sonic boom, we see and we hear.
Okay, so the sound isn't just traveling with the jet, it's being like squished into this cone because the jet is just that fast. Mind blown.
And the angle of that cone, it's directly related to the jet speed. The faster the jet, the narrower the cone.
So theoretically, if we could see sound, we could tell how fast something was going, just by the shape of its sonic boom.
That's wild. But here's the kicker. This doesn't just apply to sound.
You're right. Light plays this game too. Think about Cherenkov radiation. It's this eerie blue glow that happens when particles travel faster than light in a particular medium like water or glass.
Right, like in those nuclear reactor cooling pools. But isn't light supposed to be the ultimate speed demon? In a vacuum, yes. Nothing outpaces light in empty space. But when light travels through a medium, it slows down a bit. And that's when things get interesting. Because if you have a super speedy particle, it can actually overtake light in that medium.
So it's like a cosmic game of chicken where the light's at a disadvantage. But what's really cool is that scientists they actually use this Cherenkov radiation to measure the speed of those super fast particles.
It's an incredible tool for understanding the universe at its most fundamental level.
Yeah.
By analyzing the angle and intensity of the Cherenkov light, they can deduce the particle's speed and even identify what kind of particle it is.
Talk about a light show with a purpose. But as cool as sonic booms and glowing particles are, they're just the tip of the iceberg when it comes to how waves can surprise us. Get ready for shock waves, where the speed of a wave it changes depending on how strong it is.
And that, as Feynman explains, that is how we get those dramatic walls of pressure.
So how do these pressure waves like play out in the real world?
Think about a sonic boom again. The pressure is off the charts, right at the wavefront, and that extra oomph actually makes the wave travel faster.
So it's like the wave is kind of pushing itself along even harder.
Exactly, and because the faster part of the wave is constantly catching up to the slower part, the wavefront gets steeper and steeper.
Like a snowball effect, but with sound.
Precisely. Feynman, he gives this a great example of a sudden step in water height, like you might find in a canal. The waves in the deeper waters zoom along, overtake the slower waves in the shallows, and bam,
Yeah.
you get this wall of water.
He actually includes a diagram of this in the book, and it's seriously impressive. It's like the water just like bunches up on itself. So we've got supersonic jets creating these intense cones of sound and water piling up in canals. It seems like this piling up effect. It pops up everywhere.
It does, and it has huge implications in all sorts of fields, from astrophysics to fluid dynamics.
Okay, my mind is officially blown wide open. But are you ready to go even deeper? Literally.
By all means, lead the way.
Let's talk about what happens to waves inside the Earth. We're talking earthquakes, folks, but with a twist.
That's right. When an earthquake hits, it unleashes this burst of energy in the form of waves. But here's the thing: these waves aren't just traveling through air. They're coursing through the very core of our planet.
So it's like the Earth itself is ringing like a bell.
In a way, yes. And just like sound waves, these seismic waves, they come in different flavors. We've got our sound-like waves, which are, compressional, like those sonic booms we were just talking about.
So squeezing and releasing as they travel through the earth.
Precisely. And then we've got shear waves, which are a bit different. Imagine shaking a jump rope, that like side-to-side motion. That's what shear waves are doing.
Okay, so two types of waves, both jiggling and shaking their way through the planet. What's so special about that?
Well, these waves aren't exactly traveling at a constant speed. Their velocity, it changes depending on what they're moving through.
So like a geological obstacle course for waves.
Exactly. Dense rock.
Yeah.
Slow going, more molten material. They pick up the pace. And by studying how these waves travel, how long they take to reach different points on the surface, scientists can actually map out the Earth's interior.
It's like giving the planet an ultrasound.
Precisely. We can pinpoint layers, discontinuities, even the Earth's liquid core, all thanks to these waves.
That is wild. And speaking of wild, didn't scientists actually predict the Earth's hum just by studying these waves?
They did. It's this constant low frequency vibration, almost like the Earth is humming a tune only seismographs can hear. Feynman even includes a figure in his lecture, figure 51-7 to be exact, that shows this background hum. And get this, they predicted it years before we had the instruments sensitive enough to actually measure it.
So they knew the Earth was humming before they could even hear it? That's some serious scientific intuition.
It really is, and it gets even weirder. Remember those two types of waves we talked about, the sound-like ones and the shear waves? Well, when they analyzed the Earth's hum, they found not one but two peaks in the data.
Two peaks. So like the Earth is humming a harmony with itself.
Exactly, and that was unexpected. One theory is that it's due to subtle differences in the Earth's composition, creating two very similar but distinct resonant frequencies.
So like two bells that are almost identical but not quite. Each with its own unique ring.
A very poetic way to put it. Another theory, even more mind-boggling, points to the Coriolis effect.
Right, that whole thing where the Earth's rotation like messes with stuff.
Precisely. That constant spinning could be, subtly influencing how those waves propagate, leading to this slight frequency splitting in the Earth's hum.
Okay, now my mind is officially blown. It's amazing how something as seemingly simple as waves can unlock so much about our planet's hidden depths. But let's ride these waves out of the Earth's core and back to the surface, shall we? Because when most people think waves, they think of the ocean.
Yes. The ocean, a realm where waves once again reveal their complexity and refuse to be confined to simple categories.
Don't tell me ocean waves are about to get weird too. Everyone knows those waves. Oh, come on. You can't just like drop a line like that and expect me to not bite. What's so weird about ocean waves? They're just, big rolling hills of water.
If only it were that simple. Let's start with the basics, or what we think of the basics. That motion of water in an ocean wave, it's not just up and down. It's not just like back and forth either. It's both, all at the same time in this like mesmerizing circular dance.
Hold on, back up a bit. Are you telling me like the water isn't moving forward with the waves?
Not really, no. Picture this. Imagine you're bobbing along on a tire as these smooth swells pass by. If you could like track a nearby piece of seaweed, you'd notice it's moving in a circle, not just on the surface either. This circular motion, it goes down, getting smaller and smaller until it eventually like fades out.
Okay, so it's more like the water is doing this underwater like loop-de-loop as the wave energy passes through. That is not what I pictured happening beneath the surface. All right, so maybe ocean waves are a bit more like dynamic than they appear at first glance. But their speed's got to be straightforward, right? Big wave moves fast. Simple as that.
That's where things take another turn for the unexpected. The speed of an ocean wave, or more precisely how fast its crest travels, it depends on its wavelength.
Okay, that makes sense. Longer waves, more water moving, faster speeds. Simple physics.
You'd think so, wouldn't you? But the ocean, It loves to keep us on our toes.
Mm.
It turns out that in deep water, the longer the wave, the faster it travels. It all comes down to how the energy is distributed in those circular motions we were just talking about.
Whoa, that is seriously counterintuitive. So if I'm out on a boat and a speedboat like zips by, the longest waves from its wake will reach me first.
Precisely, those long lazy swells, they arrive first,
Yeah.
followed by the progressively shorter, choppier waves. Feynman, he even points out that you can predict all of this just by understanding the relationship between wave speed and wavelength.
It's like the ocean has its own internal clock,
Yeah.
but it's set to a rhythm we don't quite like understand. Or maybe it's more like a giant watery jazz band where everyone's like riffing on the same theme but at their own pace. This is incredible.
And we haven't even touched on what happens when these waves they approach the shore.
Oh, right. That's where things get really wild. But we've been talking about speed and wavelength this whole time. How does that all play into those dramatic breakers we see crashing on the beach?
Remember our discussion about shock waves and how they pile up on themselves. Well, imagine what happens when a fast-moving long wave starts to encounter, shallower water as it approaches the shore.
It slows down, right? So the faster waves coming up behind it, they start to bunch up too.
Exactly. That's when the magic happens. The wave it overcurves itself, building higher and higher until crash. You've got yourself a breaking wave.
Wow. I never connected those dots before. So those perfectly formed waves rolling toward the beach, they aren't just like random occurrences. They're the result of this intricate interplay of speed, wavelength, and the depth of the ocean floor.
Precisely. It's a beautiful dance between these different properties,
Yeah.
all orchestrated by the fundamental laws of physics.
And here I thought I was just watching water move around. This is blowing my mind. Is there anything else about ocean waves that'll completely change the way I see the world?
Just one more tidbit for you to ponder.
Yeah.
We've mainly been focusing on waves, driven by gravity, but there's another force at play, especially when it comes to those tiny ripples you see on the surface tension.
Right, like when you drop a pebble in a pond.
Exactly. Those capillary waves, as they're called, they actually behave in a completely opposite way to our gravity-driven friends. They travel faster at shorter wavelengths.
Okay, my head is officially spinning. Long waves fast, short waves fast. Some kind of like minimum speed in between ocean waves are anything but simple.
And to think we haven't even left the world of water yet. Feynman even touches on how those mesmerizing patterns you see in a pouring stream of milk or any liquid for that matter are also a result of waves.
Yeah.
Waves emanating from the edges of the flow, interfering with each other, creating those hypnotic swirls.
From now on, I'm never gonna look at a glass of water, a cup of coffee, or the ocean the same way again. This whole deep dive into the world of waves has been incredible. We started off thinking we knew a thing or two about these seemingly simple phenomena, only to discover they're anything but. They can be explosive. They hold secrets to the very heart of our planet, and they defy our intuition at every turn.
And as Feynman so eloquently demonstrated throughout his lectures, that's the beauty of science, of constantly questioning and exploring. It's about finding the extraordinary in the seemingly ordinary, about uncovering hidden depths in the world around us.
So to our listeners out there, the next time you encounter a wave, whether it's crashing on the shore, rippling in your coffee cup, or even just a sound wave hitting your eardrum, take a moment to appreciate the intricate dance of energy and motion unfolding before you. You might just be surprised by what you discover.